I again apologize profusely for not being able to share the slides in the other previous lecture, but you should make use of this one. So these are the slides. So the prescribed textbook that we will make use of for this quantum mechanics course will be the third edition of Griffiths. But if you have the first two editions, even that should be useful. The content doesn't really change much. If any of you are unable to use the link that I provided in the study guideline, or you are unable to get the online version from UP, you should send me an email, and I have an additional textbook that you can make use, which is, I think it's the second edition. I will also make use of these other resources. So for the last lecture, which will be on relativistic quantum mechanics, I will make use of Mesbacher quantum mechanics. I think my version is second edition, and also the Messiah. So this will be relativistic quantum mechanics. The lecture examples that I sometimes will be using, so for some of the problems, will be taken from the ZTLE textbook. It's an excellent textbook for students, especially given that it has a good balance between the formalism and also the problems. It has extremely detailed, worked out problems. And another one, which is quite longish, will be the book by Kohe, which is this one. There are 3 volumes, so which I think all in all are nearly 2,000 pages. But for this course, I will sometimes make use of the second volume. But for most of these lectures, this is the standard textbook that I will try religiously to follow. Once in a while, if any of these textbooks give a better explanation of a topic or concept, I will make use of them. But Griffiths is the standard one that I will be following. So the lectures will be on Tuesday and also Thursdays. I was planning on having live lectures, but let's say that again, let's try on this day. If for some reason again I'm unable to share the slides, then we will continue with sort of offline lectures where I will pre-record them and then you will watch them at your own pace. The test we still have to discuss, but I think once we are halfway through the course, so it will be once we have covered time-dependent perturbation theory, then during that week, then we should be able to write the test, but we still, I'll send a poll as to which day to prefer. The exam, so far as I know, it's fixed. It will be written on the 23rd of July 2021. And from the discussion we had previously, we have decided that the exam will count 50% and the semester mark will consist of 35% will come from the test, and then the remaining 15% will come from the homework assignment, which will be weekly. So the first one will be due next week Friday, but as one of you has requested, it will be made much earlier. So it will be problems what I'm going through in this lecture. So most of these quantum mechanical lectures will be on theory. So either we will be using stationary perturbation theory, then followed by the variational method, WKB, then we will consider the case. So most of these ones, what will happen will be that the perturbed Hamiltonian will just be some operator. In this example, I will use x. They're not depending on time. Maybe if you put it in an electric field, it will be QEX. But once we get to time perturbation theory, we will be dealing with things that will be depending on the time. So first, I will describe the three pictures of quantum mechanics, which will be the Schrodinger picture, the Heisenberg picture, and also the Dirac picture, Dirac interaction picture. The one that we have been using since last year is the Schrodinger picture. So in the Schrodinger picture, the eigenstates depend on the time, whereas the operator do not. But we will discuss that. And scattering. So for scattering, most of these topics are likely theoretical, and the thing that will be tying them to experiments will be this chapter. So I will define what you actually measure in a lab, which is the differential cross section, and also how to compute it using the things like the Born approximation and also the partial wave analysis. Then we'll cover symmetries and conversation laws, and then we will end the course. I'm thinking of dedicating only one lecture to relativistic quantum mechanics, and my goal in that lecture will be to solve the Dirac equation for the hydrogen atom, E and J psi, and get what these energies are. And this will tie back to what we have been doing in previous lectures, especially the lectures that we'll be doing this week. So you will see that what we are doing is that it's an expansion in terms of this parameter. So you get terms which will be proportional to alpha squared, alpha to the 4, but all these things are actually coming from the exact result, which is this E and J. So we will sort that out. So I have good and bad news. So the bad news is that the problems that we have solved so far, which will be the harmonic oscillator, right? Simple harmonic oscillator, the hydrogen atom, and also maybe the infinite potential wall. That unfortunately are the only we only have a handful of problems that we can solve analytically. Most of the problems that we get in, we will not be able to solve. So what we want to solve the Schrodinger equation. And it turns out that for most problems, we will not be able to solve this exactly. And solving this exactly, I mean, find what are the eigenenergies and also what are the eigenstates. However, there is a large class of problems where the total Hamiltonian can be written as H0 unperturbed plus some perturbation, where this we can solve exactly. So we can write the Schrodinger equation for H0 and solve it exactly, E n psi n 0. And then this would be some perturbation that once we include its effects, we are not really able to solve the full Hamiltonian. However, if this term HP is more in comparison to H0, we might be able to make use of approximation techniques. So for just bookkeeping purposes, I will put in a small number, which I will call lambda, which will be smaller than 1. So the example that Griffiths gives is that maybe if you have an infinite potential well, right? So this problem is very simple. We actually solved it. Right. So we know what are the eigenstates. Psi n is given by the normalized vector 2 over a sine n pi x over a. And we also have the exact energies, En, which n squared pi squared h bar squared over 2 ma squared. Now, suppose that we were to just put a very tiny perturbation there, right? We don't really expect these energies to change that much. So the new energies, which we denote by En, will be given by the unperturbed ones, but there will be certain small perturbation delta E plus delta E. The same thing with the eigenstates. Right? There will be some correction term delta psi. And the aim of then stationary perturbation theory is to be able to obtain what are these delta E's. Now, psi n will be depending on this small parameter, so we can do a Maclaurin expansion. So in terms of lambda say bn, we do the same thing for this En. So En as a function of lambda, can put it there. It will have some expansion Cn. So say when lambda is 0, so this will just give you psi, the original unperturbed state. There will be a term that will be proportional to lambda, which I will denote by psi, these coefficients by psi 1, which is the first order correction to the wave function, psi n, plus lambda squared, psi 2, plus dot dot dot. And then you do the same thing for the energy. So the energy will be En 0 plus lambda En 1 plus lambda squared En 2 plus dot 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 dot. And I repeat that the aim of stationary perturbation theory then will be to get what is what are these corrections En1 and En2 dot 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 dot, and also what are the correction to the wave function order by order in lambda. So this will be psi n1 dot 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 dot. So how do we do that? So the way that we do that is that we just plug everything back into the Schrodinger equation. So you know that the Schrodinger equation for the full eigenstates will be given by E n psi. The Hamiltonian actually splits into two parts, H plus H naught plus H prime, with the bookkeeping parameter lambda. Now psi n has a series expansion, so you write psi n 0 plus lambda psi n 1 plus lambda squared psi n 2 plus dot 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 dot. Then on the right hand side, En has a series expansion, so you write it out, En 0 plus lambda En 1 plus lambda squared En 2 plus dot dot dot. Again, the wave function, you expand it out, you get psi n 0 plus lambda psi n 1 plus lambda squared psi n 2 plus dot dot dot. Right. Now you just multiply everything and then you group. First, you are going to group the things that will be proportional to lambda 0. Basically, these are the that do not involve any lambda in them. Then you group to be of order lambda, then of order lambda squared, and so on. So let's start with the term that will be of order lambda 0. So this term will come once you multiply h0 there. Right? So you get h0 psi n 0. There's no other thing on the left hand side. Everything else, once you start multiplying everything out, will involve lambdas, and on the other side you just get en 0 psi n 0. And what is this? This is nothing but the original unperturbed Hamiltonian, so it means that what we are doing is consistent. Now you look at the terms that will be of order lambda, right? So this will be this h0. Once it hits there, you get 0 psi 1 n. Now let's change color. You have this term which is lambda h prime. When it hits here, you get plus h prime psi n 0. On this side, the terms will be this term in blue multiplying this one will be of order lambda, so you get en 0 psi n 1. Similarly, we multiply e1 there plus e1 psi n 0 psi n 0. And then you can check the terms that are of order lambda squared. So these terms, once you write everything out, you get h0 psi n 2 plus h prime psi 1 equals to en 2 psi n 0 plus en 1 psi 1 1 plus en 0 psi 2. So these equations are the ones that you have to use in order for you to solve the corrections. So these three equations. Now, to me, these equations, okay, this one is just a trivial unperturbed Hamiltonian, so it won't really give us much. So the things, so psi n1 is an unknown. Similarly, en1 is also an unknown. So you have two unknowns with only one equation. So this is underdetermined, and you can check the same thing with this equation. So the way that you want to solve this equation will be if you can find some state, say phi, and you hit it, and you hit this Dirac-Bra, one of these things, if this phi is orthonormal to some of these vectors, then maybe that term will cancel, and you might be left with only one equation, which may be phi, maybe h prime psi n 0 is equals to something. So the only thing that will be unknown, let's say, it will remove one of the things which are not known. So our guess for what this ket vector phi might be, the first one will be maybe, so to solve these equations, you have to specify how some vector psi n 0, what is the overlap of this vector with the new vector psi n. Now psi n 0, it's approximately, so psi n 0 of psi n is approximately the same as psi n 0. So this and original wave functions were normalized, so this has to be approximately equals to 1. However, if it's not really equals to 1, you can use Gram-Schmidt to replace this approximation by 1. So we know that 1 equals to psi n 0 psi n, and then for this psi n, you know that it has a series expansion, so you get psi n 0 plus lambda psi 0 psi 1, right? So this is the first correction, plus lambda squared psi n second order correction, plus dot 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 dot. So then this will give you psi n 0 psi n 0 plus lambda, right? This, once you multiply these two, you get lambda psi n 0 psi n 1 plus lambda squared psi n 0 psi n 2 plus dot dot dot. Now this term here, this is 1, so you get 1 equals to 1, right? So this cancels and you're left with 0 equals to. So they have to vanish order by order, so at lambda psi n 0 psi n 1 equals to psi n 0 psi n 2 plus dot 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 dot. So most of these vectors are orthogonal to psi n, to this bra. So to solve these equations, what you want to do is that hit them with psi n 0, and psi n 0 being orthonormal to most of the vectors will end up giving you the some expression. So let's try and do that. So if you look at the terms that were of order lambda, we got the equation h prime psi 1 n plus h0 psi n1 equals to en0 psi n1 plus en1 psi n0, right? This is just the equation on the previous slide, but we have found that so to solve this equation, we just go ahead and we hit it with the Dirac-Bra psi n0 psi n0 psi n0 psi n0 psi n0, right? H0 is emission, so then it will act there. Okay. Now H prime is just some complicated operator in general. We don't know how to act on the unperturbed eigenstates. We don't know how it will act on the correction, so we will just write it as it is H0 H prime psi n prime plus, as I was saying, H0 when it adds there will just give you an E0, and you can take it out because it's just a C number, so you get En0 psi n0 psi n1 equals to En0 psi n0 psi n1 plus E1 psi n0 psi n0. Original wave functions are normalized, so this is 1. these are either orthonormal, so this is 0. If you don't want to use that argument, then they are orthogonal, but this term will cancel with this term. So you are left with psi n 0, h prime psi n 0. Why did I put 1 there? If you look at the equation in the previous slide, I'm 100% sure this is 0. Right. So this gives you E1, and we're done. Now we have obtained the equation that Griffiths calls the most important equation in quantum mechanics. So basically what we have shown is that to get the first order correction to the energy, nth energy, all you have to do is just sandwich psi n. So you just compute the expectation of the perturbation using the unperturbed Hamiltonian. It's this simple equation. Right. So in the example that Griffiths gives, you start with the usual infinite harmonic oscillator, but the floor has been raised. So you've raised the energies by some perturbation h prime, which is just v naught, and then the question will be what is the change in the energies. So the first order correction will be given by psi n 0 v psi n 0, which will give you, now this is v naught, right, which is just a constant, so you can take it out, v naught psi n 0 psi n 0, and this is 1, so this just gives you v naught. So to summarize, the change in the energies will be by n squared pi squared h bar squared over 2m a squared plus v naught, and this is exact. You could, however, had not really the other example would be you only change it slightly, so you raise the floor only between 0 and a over 2. And between a over 2 and a, you leave it as it is. Right? And what is the change in the energy for this one? So we use the same formula En. It's going to be given by psi n 0 v. If you want, you can call it h prime psi n 0. This will give you, now you have to integrate from 0 to a over 2 v naught, I write everything out, psi n of x v naught psi n of x, which will give you 2 over a 0 a over 2 sine squared n pi x over 2. The v naught you can take out, so this gives you v naught 2 over a 0 a over 2 half 1 minus cos n pi x over a with a 2. So once you replace this just gives you sine n pi, which is 0, so this doesn't contribute, and you are left with v naught 2 over a half A over 2. So that cancels. This works out to be V naught over 2. So remember, to solve the Schrodinger equation, you have to specify En and also the wave function. So we still have to find what are the correction terms in the wave function. So to do that, you use this trick that you write psi n1, write this as 1 multiplied by psi n1. The original eigenfunctions were not only orthonormal, but they are also complete, meaning that 1 is given by psi n 0, 0. So you just plug it there. So this gives you m not equals to n of psi n 0 psi m 0 psi m1. And this is just some complex number, it's just a C number, so you can rewrite this as m not equals to n. M not equals to n doesn't really contribute because you already know that psi m0 and psi n1 are orthonormal, but I don't want to be carrying around a zero null state all over, so I'll explicitly say that m is not equals to 0, even though m not equals to n doesn't contribute, because we have shown that, remember this condition, lambda psi 0 psi 1 n equals to psi n 0 psi 2 n equals to dot is equals to 0. So, but the point of this rewriting is that in order for you to get the correction to the wave function, you first have to compute what this number is. Psi m 0. And to get that overlap, what you do, if you go back to the expression, the lambda order term, for you get h prime psi 0. Remember what we're looking for. We're looking for this C number, which is psi m 0 psi n 0. And if you look at the term of order lambda plus h0 psi n 1 equals to E n 1 psi n 0 plus E 0 n psi 1 n. So this is the expression that you will have obtained once you expand everything and group the terms that will be of order lambda. Now you're looking for this overlap. It's easy to see what you have to do. You just have to hit everything with the Dirac-Bra psi m 0. So hitting that psi m 0, psi m 0, psi m 0, psi m 0. what do we get? Now H0 again is the same argument. H0 will be Hermitian, so it will be acting on there, and it so this term will give me EM0 say psi F0 psi N1 plus H prime psi N0 psi M0. This is a C number, so you can take it out of the envelope. En1 psi M0 psi N0 plus En0 psi M0 psi N. Right. So we're looking for that psi M0 psi M1. The null vectors psi will null, so this where this f not equals to n comes in, so it's not equal to n, so this gives this term gives you delta m, and m is not zero, m is not equals to n. A prime psi N0 equals to, you take this on this side and then you put the difference En0 minus EM0 psi M0 psi N1, and then we can solve for this. We just by the energy difference. So I have been able to